Welcome to this video, where we will explore one of the most famous and mind-bending ideas in quantum physics, Heisenberg's uncertainty principle. This principle reveals a fundamental limit to what we can know about the properties of particles, and it challenges our everyday intuition about precision in measurement. Today, we'll explain the uncertainty principle in simple terms, show why it matters, and explore its implications for the quantum world. In classical physics, we are used to the idea that we can measure things as precisely as we like. If we know the exact position of a ball and its exact speed, we can predict where it will be in the future. This determinism is the cornerstone of classical mechanics. There is no fundamental limit to measurement. With better tools, we can always measure more accurately. Quantum physics, however, tells a very different story. At the microscopic scale of atoms and subatomic particles, nature imposes limits on what we can know. Werner Heisenberg, in 1927, formulated what we now call the uncertainty principle. It states that certain pairs of properties, like a particle's position and momentum, cannot both be known precisely at the same time. The more precisely we know one, the less precisely we can know the other. To understand this, imagine trying to measure an electron. If we try to determine its exact position, we must interact with it using light or some other probe. But this interaction disturbs the electron's momentum. The more we focus on its position, the less we know about how fast it is moving and in what direction. Conversely, if we measure its momentum very precisely, its position becomes more uncertain. This is not a limitation of our instruments, it is a fundamental property of nature. The uncertainty principle applies not only to position and momentum but also to other pairs of quantities, such as energy and time. If we try to measure the energy of a particle precisely over a very short period of time, the measurement itself becomes uncertain. This shows that uncertainty is woven into the fabric of reality, not just a result of imperfect measurement. A simple analogy can help illustrate this. Imagine a spinning fan in a dark room. If you try to capture a photo of the fan's blades using a very short, sharp flash of light, you can see exactly where each blade is at that instant, but you cannot tell how fast the fan is spinning. If you take a long exposure photo, the motion of the blades is clear, but their exact position at any moment becomes a blur. The more clearly you measure one aspect, the less precisely you can know the other. This is similar to the uncertainty principle, although in the quantum world, the limitation is absolute, not just practical. The uncertainty principle has profound consequences. It tells us that particles do not have perfectly defined properties until they are measured. Unlike classical objects, which have a definite position and momentum whether we observe them or not, quantum particles exist as probabilities. The uncertainty principle also explains why electrons do not spiral into the nucleus of an atom. Their position and momentum cannot both be precisely defined, which creates a natural stability in atomic structures. Heisenberg's principle is also central to many quantum technologies. It limits how precisely we can measure particles in experiments, but it also enables innovations like quantum cryptography. The principle ensures that any attempt to observe a quantum system inevitably changes it, providing a basis for secure communication methods where eavesdropping is detectable. The philosophical implications of the uncertainty principle are equally profound. Classical physics assumes a deterministic universe, where the past and future are fixed and knowable. Quantum physics, guided by the uncertainty principle, tells us that at a fundamental level, nature is probabilistic. We cannot predict exact outcomes, only probabilities. This challenges our intuitive sense of reality and forces us to rethink notions of causality and measurement. In summary, Heisenberg's uncertainty principle states that certain pairs of properties, such as position and momentum, cannot both be known precisely at the same time. The more accurately we know one, the less accurately we can know the other. This principle is not due to imperfect instruments, but is a fundamental property of the quantum world. It explains the behavior of particles, the stability of atoms, and the probabilistic nature of reality. By understanding the uncertainty principle, we gain insight into the limits of knowledge at the quantum level and the strange, counterintuitive behavior of the microscopic world. It is one of the key concepts that separates classical physics from quantum physics and forms the foundation for much of modern quantum theory. Thank you for joining this exploration of Heisenberg's uncertainty principle. As we continue to study quantum mechanics, this principle reminds us that nature operates in ways that are fundamentally different from our everyday experience, revealing a universe filled with probabilities, mysteries, and unexpected possibilities.